Hi, everyone. I'm Kendrick, and I'm going to talk about our paper on parity violation in BOSS. I'll just give some definitions and then hand over to Simon and Alex for the analysis. A couple of years ago, some papers found some really exciting evidence for parity violation in BOSS. There was a paper by Slepian and Kahn that got up to 7 sigma with certain choices, and a paper by Oliver Philcox that got up to 3 sigma. In this plot, we've reproduced the 7 sigma result with our pipeline. The point of the slide is just that there's a statistic called chi-squared, which is sensitive to parity violation. The value of chi-squared on the BOSS data, shown by the red line, is an outlier compared to the mock headlogs, shown as the blue histogram. I want to talk about how chi-squared is defined. It's defined in terms of two building blocks. There's a quantity EA, with a vector with 18,000 components, where each component is a parity-odd 4-point estimator. The components differ in the angular dependence and length scales of the 4-point function. And then the other building blocks is C, an 18,000 by 18,000 approximate covariance matrix, which is only used for data compression purposes to reduce the vector quantity E to a scalar statistic chi-squared. Chi-squared is a parity-even H-point statistic. It's more like the variance of the 4-point function. The motivation is that it avoids assuming a theory template or even preferred sign for the 4-point function. In the absence of a preferred template, you're forced to square components and then add them together since there's no preferred component. So I claim that if you see an excess in chi-squared, there are two possible explanations. You can have parity violation, meaning that one or more components of E is non-zero on average in our universe. But then the other explanation is that the mocks just underestimate the covariance of E compared to the data, leading to an excess chi-squared. The main methodological result of our paper is new statistics, chi-squared cross and chi-squared null, which distinguish these two hypotheses. The way the statistics work is that we are going to get independent estimates of EA and compare them. The way we get those independent estimates is to divide BOSS into geometric subregions. So we split BOSS into n patches, where n is 3 in the north or 2 in the south, with some padding in between to make them statistically independent. We estimate the parity-odd 4-point function EA in each patch. So it gets an extra index mu that goes from 1 to the number of patches. And then chi-squared cross and chi-squared null are defined similarly to chi-squared, except that in chi-squared cross, we just cross-correlate patches rather than squaring. And in chi-squared null, we take differences of patches and then square. The intuition behind these statistics is that chi-squared cross is like a cross correlation between 4-point functions, and chi-squared null is like a null test that's sensitive to differences in 4-point functions. So now if you imagine that parity violation, the parity violation hypothesis is correct, then what would happen is you would get a contribution to chi-squared cross, since you would have 100% correlated 4-point functions in the different patches. But you would not get a contribution to chi-squared null because it would cancel. Conversely, if you imagine that the covariance of the data doesn't match the mocks, then the parity-odd 4-point function would be uncorrelated between patches like random noise. So there's no contribution to chi-squared cross, but you would still see the excess covariance in chi-squared null. These intuitive arguments can be backed up by formal calculations. In a short talk, I won't walk through the formal calculations in detail. I'll just refer you to section 4 of our paper, except to say that you can just turn the crank and calculate the excess in the original chi-squared statistic, and you find two terms: a parity violation term, which is non-zero if the expectation value of EA is non-zero in our universe, and then a covariance mismatch term, which is non-zero if the covariance of the data differs from the covariance of the mocks. If you do the same calculation with the new statistic, then in the case of chi-squared cross, you get the same parity violation term with no covariance mismatch term. And in the case of chi-squared-null, you get the covariance mismatch term, same term, without the parity violation term. So that's the formal sense in which the original chi-squared statistic is a degenerate combination of these two signals, and the degeneracy is broken by the new statistics. And with that, I'll hand off to Simon for the next part.
Hi, I'm Simon, and I'll talk a little bit about the so-called analytic covariance that appears in the statistical analysis. So Kendrick already mentioned the 4-point correlation function here with all its different indices. And I'll now talk about the covariance of this 4-point function. As shown in Ho et al. 2023, this covariance can be calculated analytically if two conditions are met. The first one is that the galaxy field should be Gaussian, and the second that the survey geometry is a 3D periodic box with the volume that we call V fiducial. And the analytic covariance is just what we call the covariance of the 4-point function with these assumptions included. Now, these assumptions should not be intended as accurate approximations, and the analytic covariance should also not be thought of as a good approximation of the covariance of the actual data. But like Kendrick mentioned, it's used for data compression. Since this 4-point function has something like 18,000 components, we need to define statistics like the chi-square or the related ones that Kendrick introduced. And the analytic covariance is just a part of the analysis that needs to be computed. Right, now I'll say a little bit about the inputs that go into this. First is a galaxy power spectrum and a Poisson noise term. And in this case, this is generated by class PT, and the Poisson noise term is just a constant. Second, there are two numeric parameters, the Poisson noise that I just mentioned and this fiducial volume. And these are different for each data set. We just take them from the previous analysis to make sure that we are comparing everything as directly as possible. And the rest is really just some numerical integration parameters. So first, there are some integrations in k-space that show up, for example, for some correlation functions, like this standard 2-point function here. And second, there are integrations over R, over products of these correlation 2-point functions. And with our choices, we follow Ho et al. 2022 as closely as possible, again, to be able to compare directly. Right, and it can be shown that this is what the computation of the analytic covariance looks like. It's basically just the sum of these different T and U terms and with different permutations of the indices. Now, since the 4-point function had 6 indices, the covariance now has 12 indices. And just roughly what, most straightforwardly what you would have to do is for all indices, Li and beta I, where Li are these spherical harmonic indices ranging from 0 to 4, and beta I are the radial bins. For example, you could have 10 or 18 of these. Now, for all these indices, you would have to compute T and U. And for each of these, again, there are some combinatorial factors that show up. Then there are also the 2-point functions that I mentioned. And for each of these, again, you have to compute binned and unbinned Bessel functions and integrate them over K. Now, this gives you the 2-point functions. And the products of these, you now have to integrate over R to get a single T or U. And now you have to get a bunch of these T's and U's for each of these indices. And now I'm not going to get into this, so feel free to pause if you want to look at this, but this is what the T's and U's look like, and here are the definitions of the 2-point functions, where again the psi is just a normal 2-point correlation function. And so we wrote a public code to do this. Here's the link. So the individual parts of these computations are pretty straightforward, but actually because of all these indices that you could see, things become very messy and it's very easy to make mistakes. So we try to be as simple as possible in the implementation to ensure correctness. But also, on the other hand, depending on how many tricks you use, and we try to use not as many, again, so things don't become too complicated, this computation is actually quite expensive. So we had to make use of caching and parallelization to deal with that. And we also designed it to be able to easily do numerical stability and convergence tests. Because when we started looking at this question, of course, we didn't know where the parity violation signal was coming from, and we wanted to make sure that it's not part of this really complicated computation. Right, and we have some convergence tests, which basically confirm that what the previous analysis did was fine. We also compare it with the pre-existing code in the parity-even case and the output from previous analyses, and we have very good agreement. So we're very confident that this all is working correctly and nothing strange is going on. Yeah, the references, and if you want to pause.
I'm Alex Krolewski, and I'll tell you about the data and results for our work on the reanalysis of parity violation in BOSS. Exactly following the previous papers, we use the publicly released BOSS DR12 data with the default weights. These weights correct for instrumental effects such as imaging systematic and fiber collisions. Following similar tests in Jamin's paper, we test the sensitivity of the detection to these weights. There's a small technical detail about exactly which sample we should use to study these galaxies. And basically, it boils down to whether we should select the galaxies by targeting algorithm or strictly by redshift range. But in the end, we find that our results are quite robust to this choice. We also need to compare the 4PCF from data to mocks. And to do this, we use the patchy suite of mocks. These are approximate n-body simulations with some galaxy bias parameters that were tuned to reproduce the BOSS two-point function and approximately match the three-point function. The right-hand panel shows this three-point function comparison, which is overall quite a good match, although you can see some disagreements, especially in this top panel, which is looking at relatively smaller scales. The basic idea behind our pipeline, which Kendrick has already described, is that we want to compare a parity-odd sensitive statistic between the data and these 2,000 patchy mocks. The previous work used this chi-square statistic, which unfortunately has contributions from both parity violation and from the possibility of a data mock mismatch. If the mocks underestimate the variance in the data, then you might think that you have a detection, but in reality, all you've done is underestimate your error bar. And this possibility was noted in these previous papers. So in our work, we use the chi-squared cross statistic to isolate parity-odd detection from data mock mismatch, which we can characterize with chi²-null statistic. And these new statistics are much less sensitive to data mock mismatch. And in particular, this data mock mismatch would cause an additive bias in the chi-squared statistic, but it'll only cause a multiplicative bias in chi-squared cross, which is expected to have mean 0. To measure the parity-odd 4-point correlation function, we use the publicly available Encore software, and we match the settings of these previous papers using both the SGC and NGC in the redshift range 0.43 to 0.7. Here I'm showing the patches that we've defined to use chi-squared cross. We chose some padding to decorrelate these patches. So the padding is approximately 100 megaparsecs at the lowest redshift range of interest, such that there will be minimal correlation between galaxies and neighboring patches. And in fact, we explicitly test this. We test that, indeed, there really is no correlation between these patches. They are sufficiently far separated. Another thing to note is that the galaxy properties are very similar between the patches. So here on the top right, I'm showing the redshift distributions, which are a little bit different between NGC and SGC, but are very similar in the patches. And essentially this large-scale homogeneity has also been tested by the BOSS team. Okay, so the first step is we need to make sure that we can reproduce the previous work. And here I'm showing the distribution of the chi-squared statistic in the data in red and in mocks in blue. And we ran both the 10-bin case, which is reproducing Oliver Philcox's work, and the 18-bin case, which is reproducing Jamin Hao's work. And you can see, we have a very robust detection in the 18-bin case and a rather less significant detection in the 10-bin case. And over on the right, I'm reproducing a table from our paper that shows the number of sigma of these detections. We're matching quite well to previous work. And below the top line, I've also shown a number of different baseline systematic tests. So we swapped the sample CMAS versus CMAS low Z total. And then we checked what would happen if you turned off the weights. And consistently with Jamin's analysis, the parity violation signal does not go away when we make any of these changes. The detection significance does move around, in some cases rather significantly, but in no case is there nothing detected. All right, so then we want to apply our new statistics to the data. So we'll start with the chi-squared distribution that was used in the previous work. And here we're mainly going to consider the 18-bin case, reproducing Jamin's work. And so you see here, there's a strong detection of parity-odd signal in the chi-squared statistic. However, when we go to chi-squared cross and chi-squared null, that detection significance goes away. And here you can see that the data now lies well within the distribution of mocks in chi-squared cross, and much less than the expectation if that chi-squared parity violation signal had held. We can visualize the ability of our new analysis to break the degeneracy between parity violation and data mock mismatch. The red contours display the previously used chi-squared analysis, and here parity violation and data mock mismatch are entirely degenerate, hence leading to the diagonal line. In our work, we can break this degeneracy by constructing both chi-squared cross sensitive to parity violation and chi-squared null sensitive to data mock mismatch. And as you can see from the blue contour, our analysis favors a much reduced detection significance of parity violation and a strong detection of data mock mismatch. One final question is what to do about the combination of SGC and NGC. So previously I had shown you the results for the NGC region. We obtained similar detection significance in SGC. So naively, if you just took the two chi-squared statistics and added them in quadrature, you would get a 2.5 sigma detection. However, there are a number of other things that you could do instead to combine the two hemispheres. So for instance, you could do a 5-patch chi-squared statistic where you consider cross pairs between SGC and NGC. And this reduces the parity violation signal, but it also considerably reduces the error bar because you have many more pairs to consider. In this plot, we show various different ways of doing this combination, all of which we think are relatively reasonable. And they don't quite agree with each other. There's a bit of a dispersion between nothing in this fourth case or up to a 2.5 sigma detection significance. And so I think the overall message here is that in all cases, the parity violation signal is dramatically reduced from what it had been previously. It's gone from 7 sigma in the chi-squared analysis to about 2 sigma in this analysis, no matter which way you choose to combine the hemisphere. So with that, I would just like to leave up our conclusions. To sum up, the chi-squared statistic previously used is sensitive to parity violation, but it also has a bias if the parity-even 8-point correlation function of the mocks doesn't match that of the data. So we devised and measured new statistics which can separate this parity violation and data mock mismatch explanations and allow an unambiguous conclusion to be reached. When we apply these new statistics to BOSS, the statistical significance of the parity violation signal goes from about 7 sigma to about 2 sigma. And this is not direct evidence for systematics in BOSS. It's just showing that there's a disagreement between the 8 PCF of mocks and data. And so in the future, we have some proposals in the paper for how to remove the dependence, the rather arbitrary dependence on the choice and number of patches. And we're also quite excited about applying these new statistics to new data sets. DESI is incredibly powerful and already has basically as many spectra as SDSS in its first year. And so this will be quite exciting to see what happens with this new data.